So in this example number 2, we are going to review how the derivatives work both in Cartesian and polar coordinates. Let's consider a small particle of air moving in space. Okay, and the first exercise we want to do is we want to work this in the Cartesian coordinate. And let's put our axis is x, is y, is z, and I have the particle location right here. And what I know from the problem is that the particle is at a distance y, a distance x, and a distance z. Okay? But given this, I want to know what is the position vector, the velocity vector, and the acceleration. Okay? So r is equal to xi plus yj plus zk, right? Because the distance is that this is actually particle moving in space, in the air moving in space. Now, if I want to know what is my velocity, I just have to take the vector and divide that by time. Okay, so if I did that, you can just show this is equal to the derivative of time plus derivative y respect to t plus derivative of z respect to t respect to k. If you wanted to know your acceleration, the acceleration is nothing else than the derivative of the velocity respect to time, and that would be the second derivative of x respect to t plus second derivative of y respect to t plus second derivative of z respect to t squared k. Okay, so those are the equations in Cartesian coordinate, and it's quite straightforward. It's a lot easier to work with. Now, I wanted to consider the case in which it's the same point, same location, but we want to represent all this, but not in the Cartesian coordinate. I want to represent all this in the cylindrical coordinate. Okay, so in the cylindrical coordinate, well, what we have is a vector r, and this is moving theta, and we have our distance z. Okay, so z remains. So in this particular case, your new position vector now looks like this. Your position vector is r times e, r, right? Because the total distance this moves in this direction, and plus it is z times e z. Okay, so this is your r, and this is how much it moves in your z direction. That's why cylindrical coordinate or polar coordinates are easier to work with many times. Now, the problem is when I want to find the velocity. The velocity is a little bit more trickier than you think it is when I take all these components with respect to time. The first, note the following. dr respect to dt times er plus r times dr respect to t. This is important. I'm going to explain this in a minute. It works very different than when you work in Cartesian coordinates. Because everything is working at 90 degrees, is rotating in 90 degrees, so all the orthogonal terms are actually equal to 0. In this particular example, no. Okay, in this particular case. So first of all, this is at 90 degrees. That's why it's moving in 90 degrees in this direction. So this particular term right here, your delta Ez is actually equal to 0. Okay, but now you have an extra term here that you did not expect, is this term right here. What do we do with it? Now, if I may suggest you, this particular term, where does it come from? This term, if you realize, consider this. What is dr respect to d theta, right? So dr d theta is nothing else than the tangent of this location. So that means that is actually d theta unit vector d theta. But I'm taking the derivative of this respect to theta, and I'm finding what the slope is in this direction. So that's actually equal to this. Okay? Or I can say from here, this is equal to e theta times d theta. Okay? So now if I plug everything inside here, let's see what we get. You get dr d theta er, and then you get plus r d theta, because you got a theta here, dt times e theta plus dz times dt times ez. So this would be actually your velocity in cylindrical or polar coordinates. Okay, so now what you can realize that when you're working in Cartesian coordinates, this is actually equal to 0. Why? Because anytime this respect to t, the delta t, this is 0 because these are all mutually orthogonal axes. So this is actually, they cannot be this. There's all 0. In this case, this is not necessarily at 90 degrees, but it depends on the slope of that. That's why you got this extra term floating around in this particular case. Okay, so this concludes this very topic on example number 2 on vector calculus.